Our next speaker is Eleanor Schofield from the Mary Rose Trust in Portsmouth, and she will discuss with us how synchrotron techniques can help us understand and preserve maritime heritage.
Right, so good morning, everybody. First of all, thank you to the organisers for giving me the opportunity to talk, and also for giving such great introductions yesterday to the techniques, most of which I'm going to show in this talk, so it means I can focus on the results and not how to do the experiments. Also, thanks to many of the speakers that have already gone, because I'm going to try and touch on quite a lot of themes that have already been talked about. Namely, things like some of these techniques are really powerful, but you need to know what you're looking for. Also, they might tell you what is there, but not necessarily where it is. And that sometimes in sampling these things, you can mess with that. It might not be giving you a representation what is there in your 3D matrix, whether that is a fossil, whether it's a painting, whether it's an archaeological object in this case. And last of all, making sure that whatever we are doing is for the benefit of that collection, whether it's looking after it, whether it's telling that story. So my background is actually material science and synchrotron science, and I find myself now working at the Mary Rose. And so a big part of what I do is making sure what we're doing, even if it's many steps off and many years away, it is to look after that collection. Now, onto the collection. Can I just ask for a quick show of hands of who has heard of the Mary Rose before? That's good, because I'm going to give you a very short introduction so I can get onto the science. So this was a ship of Henry VIII. It sailed for over 30 years before it tragically sank in 1545. The collection that we have is because it was preserved under the seabed for hundreds of years until it was found, and the remains that we have of the ship were excavated in 1982. Alongside that, we raised over 19,000 objects. There is a huge range of objects in terms of what they were used for, so we have very personal objects. We have everyday equipment such as cooking items, things like that, and obviously weapons. They really vary in terms of their size, how they're degraded, and also the different types of materials. So as a material scientist, this collection keeps me very busy. So I first started working with the Mary Rose when I was a researcher at the University of Kent. We were looking at the problem of sulfur in marine archaeological wood. We've heard a lot about sulfur already, the many different states that it can occupy and how damaging it can be. Here you can see a chest panel, and also on the right is where an iron bolt once was in a gun carriage, and you can see there are all these salts which don't look very good, but they're also very damaging. Now, the wood itself, the ship is in very, very good condition considering everything that it's been through. But typically with these materials, you do have to do some kind of consolidation treatment to compensate for the loss of the wood material. In our case, we treated with polyethylene glycol, and once that treatment was finished, we then needed to dry it to remove any residual water. Now, obviously, the worry with that was we were then going to expose it to air, to oxygen, and we knew that sulfur was in the timbers and that this could transform and cause us problems. So we set up a program of work at Diamond Light Source at B18 using sulfur zanes to monitor what was happening to that sulfur as we were drying it. So the pictures here show you part of the ship and show you the kind of environment when the sprays were on and then when they were off. And then what I'm showing here is the sulfur zane. So you can see from this core sample that we've taken to the beamline, when the sprays were on, there was very little oxidized sulfur there. But then as we turn the sprays off, you get much more oxidized sulfur on the surface and it developing into the wood. We then came here to ID21 and we took those same core samples and took very thin sections of them to try and map what was there. So we had a couple of explanations yesterday about how you can XRF map at different energies to show you where the different oxidation states of sulfur are. So in here, the green on the left is the surface before we started drying, and on the right is after we started drying. The green is the reduced sulfur, and the blue is the oxidized. So you can see straight away that there's much more oxidized sulfur. And then at the points indicated here, we've done zanes to work out exactly what is there. And by also measuring our standards, we can then do quantitative analysis to work out the different proportion of materials that are there. So this is all great. It's very informative. It's told me what is there, but I still don't really know where it is within the 3D structure. So this brought us back to the ESRF to ID 15. First of all, what I'm showing here is tomography. So this is the absorption tomography. We look at this against fresh oak. So in the fresh oak, you can see the wood structure, you can see the vessels, you can see the growth rings. In the Merrose samples near the surface, you can see that it's just a bit chaotic. That's because it's degraded. A lot of the wood structure has been compromised. But as you go down into the surface, you then start to regain some of that structure as the wood is less degraded. Now, what's fabulous about ID15 is that at every voxel within that tomograph, you can take PDF analysis. Now, PDF, very briefly, as opposed to XRD, is going to tell you about all the nanocrystalline and amorphous phases that are there. So what we're able to show here, this is a slice through a core sample. So on the left, you have everything that's there. What I really love about these images too is that you can see the growth rings, and you can also see that how either the plank or where we took the sample is obviously not straight on, it's slightly off. And then you can isolate different phases. So what's great about this is it's telling you everything that's there. You just then have to find the match to what it is. So we knew that PEG was there, so sure enough, we can see it more near the surface and where the vessels are. We then found some really interesting things. So on the right-hand side, we found this nanophase. This comes out as this matches with a zinc blend, so it's a zinc iron sulfur. You can see that they're not actually near the surface, they're kind of like a tier down. So perhaps they did form at the surface and they've been washed out, we're not sure. But this is really powerful at telling us what's there and where it is in the wood. We actually have other phases as well, which we haven't managed to match to anything yet. So this is an ongoing process to understand what we're dealing with. We talked yesterday about how it's very important to do your characterization before you come to the beamline, but the reverse is also true. So what we've learned at the beamline, we can then go back to the lab and think, right, well, how can we further our understanding with that? So this is one of the same core samples that we ran all these experiments on. But here we wanted to look at just benchtop XRF and also FTIR. So FTIR is really powerful with the wood because you can look where it's degraded, because you can distinguish the lignin from the hemicellulose and cellulose. And the latter two are the ones that degrade preferentially. So you see a much higher proportion of lignin where it's really degraded. And sure enough here, you can see the core at the top, you see where it's darker. This matches with where it's more degraded, where there's sulfur and iron, but also where there's zinc. So this is another kind of indicator that zinc is playing a role in this. So this took us back to the beamline. So as I was saying at the beginning, you need to know what you're looking for. So we had this program of years of work at Diamond looking at sulfur and iron. We weren't looking at zinc because we didn't know we needed to. This is a kind of very rough and ready graph because we literally took this data a few weeks ago. But you can already see all the different sets of data at different depths into the wood, and you can see that there's different phases there, or different compounds there. So we will be doing some work now to try and work out what they are and where they came from. We are also seeing some problems with sulfur in other materials. So we have thousands of bricks in our collection, which can often be quite surprising to people. But this was the ballast, but also made up the galley. So there were 2 galleys on board the ship. And you can see the kind of salts that form, particularly when the artifacts are in high humidity. And these are SEM images that we took. This properly was a moment where I had to forget being a scientist, because when I first looked at these, I was like, wow, these images are beautiful. They're actually incredibly damaging for the material, so this is not good news, but they are beautiful images. And you can see that there's sulfur and there's calcium and there's iron there. We have done some SEM EDS analysis. What's interesting is the conservation treatments that were done on these were cascade washing to get rid of sodium chloride, because that was known to be there. Nothing was done for sulfur and iron and things like that because it wasn't known that they were there. And these treatments were done back in the kind of 70s, 80s. I've put a question mark as to what technique we'll do with it, but I know, so we did some lab XRD, but because there's so many different phases there, you didn't get the resolution to be able to deconvolute what was there. So again, a few weeks ago, we went to I-11 at Diamond Light Source and did some diffraction there, and we're just figuring it out at the moment, and I don't have the data yet to show you, but hopefully next time I see you all, I will. Just very briefly to mention the fact that some of the work that we do, and this is a project in its very early stages, is as much as we love beam time, this was touched upon yesterday, is you don't always need to come to the synchrotron. It's also very competitive, as we know, and you don't always have the people with the expertise at a museum. I mean, I happen to have a background in synchrotron science and I'm at the Mary Rose, but it's not necessarily true that the Mary Rose would always have somebody with a synchrotron background. And what we wanted to do, I'd read some studies looking in environmental science where they'd use sulfur electrochemistry to detect sulfur in the different states of sulfur. So what I'm showing here is how we use the synchrotron to analyze FES2, and then we made a pellet of wood to kind of mimic chemically the environment we have in the Mary Rose wood. And what we did was then look at the electrochemistry from that in solution, and you can see a similar pattern here. So again, it's in very early stages, but the overall aim is that we would essentially have a system where you could do it in situ. You won't need to remove artifacts. It would be very straightforward, and you would have an indicator of there being some problematic sulfur there. So on to the Mary Rose Cannonball. So marine archaeological iron is very complicated and can corrode very badly due to the chlorine from the salts that's there. This shows you how badly it can corrode. Some of them actually are in complete pieces. They literally just explode. So we've done a whole series of experiments over the last 4 years looking at different synchrotron techniques to understand the different conservation treatments that have been done. For example, we have XRF maps where we've taken sections of the shot and we've looked at where the chlorine is. Sometimes it'll be scattered throughout at the surface. For some of the treatments, you'll see that you'll just get little inclusions inside. And when we look at the spectroscopy of that, you actually get different phases. So sometimes it's something called a cagonite, which is a very typical, very damaging corrosion product. In other cases, particular inclusions inside, you'll find that it's a precursor to that product, and it will only form given to the right conditions, the right solutions, the right pH, things like that. We've also done, yes, it's working. We've done tomography. This was at I-12 at Diamond. So first of all, just visually looking at this. So this is a segment about this big. So the darker phases are the corrosion. You can see where the cracks are. You can see where the surface is. So this is obviously just showing you it as a whole. And then on the right-hand side, when that kicks in, you can see it layer by layer. So we can start to understand where the corrosion is. And then we can separate those phases, so we can look where is the metal, where are the cracks, where are the corrosion, and how do they exist in relation to each other. And then the last experiment that we've been doing on the iron, this is on I-11 at Diamond. They have a back hutch, which is for long duration experiments, so we've been running this for well over a year. Here you see robotic arms, and there's a whole range of different experiments there, and they have every Monday blocked out that they will put each of those experiments in the beamline and run X-ray diffraction on them. So we set up an experiment where we were looking at marine archaeological iron, Mary Rose iron, some freshly excavated marine archaeological iron, some modern day equivalent iron, and also some synthetic acagonite. We put it into a solution which is typically used as a passive solution for looking after these kind of materials. And then every week we've been collecting diffraction patterns. And all of this data is being looked at now, but just to give you an idea of the kind of thing we can get from this, this is the freshly excavated iron, and the peak that's highlighted there is this very damaging product, acagonite. So you can see over the hours, as it's exposed to this solution, how that starts to form. We can then do refinements on this data and look at the weight percentage of the different phases there, and you can see over time that you've got quite a lot of acagonite, and then that does tailor off. It transforms into something else over time. And then very quickly, the last thing I wanted to mention is actually I haven't been involved in this research, but it's research that was done with a former colleague of mine. All the people involved are at these institutes here. And what they did was use the Xmas beamline here to do X-ray diffraction to look at some of the copper alloys, the brass links, and look how different conservation treatments had affected them. So in the bottom pattern, you see here that you get a peak not only from the brass but also from copper, so this shows that the surface has undergone some dezincification. You can also see the one in the middle where it's much cleaner compared to the top one. The top one has much more corrosion products, and you can actually correlate this to the different treatments that were done to it, the different levels of cleaning that it underwent. So I've mentioned lots of different projects there. It's involved so many different people at different institutes. I hope I've put them all on here. All of this is only possible because of their interest and their passion for our collection. I can't give any talk without encouraging you all to come and visit our museum. We are not far from London. Thank you for your attention, and I hope to see you all at the museum soon.
Thank you, Eleanor. We have some questions.
Coming from Sweden, of course, I'm interested in how this relates to the conservation problems of the Vasa, where a very similar approach with polyethylene glycol was used, but you have another runtime about 20 more years, so you can see how the thing progresses. So, I mean, do you have some sort of like collaborative interactive thing with them?
Very much so. So yeah, they were a step ahead of us, and there's certainly things that we we learned when planning our conservation treatments, they had used different grades of PEG and they'd learned things about that, so we implemented that. And even to this day, we look at the different ways that things are changing, and there's lots that we can collaborate on. There's ways by using the polyethylene glycol, there's ways in which that can affect the mechanical properties of the wood, and they're doing a lot of work on that, and we're starting to now as well. So, yeah, it's a very, very good partnership for us to have.
That's very nice here. Just one other question. With the degradation of the wood, where's the zinc coming from that's causing you trouble? Is it leaching out of the brass items? Or it seems a rather odd sort of element to get turning up in this context.
Doesn't it just? Yeah. I think there's a variety of places where it can come from. You do have the same with the sulfur. You have bacteria that will interact with it in the seawater, so that's a possibility. It's possible from the artefacts. What we're also looking into is everything that's been done to the ship and is around the ship, so the supports that it's on, the treatments that it's had, so we're really having to go through everything. But that's what the recent analysis will help with. We'll be able to point exactly what compounds are there and then try and figure out where it came from. But yeah, it's an interesting find.
Well, thanks very much.
We have another question. Yes, already.
So I think you mentioned this PDF activity at ID 15, I think it was. So could you elaborate a little bit on some details and maybe on constraints you have to respect to use that method, so in terms of how small or how big samples can be?
I'm not entirely sure of the size of the sample. We had very small samples, but I think there are bigger samples that you can fit in there. I don't know if Marco is here actually from the Beamline. I think maybe not. He would be able to answer your question much better than I can. There's certainly it's the age-old thing of balancing the size of the sample, how long it will take, and the resolution that you want to go for. The data that I showed, we were leaving those samples in for kind of half a day, and you would be able to get that kind of 5mm core, and it was about 5-10 millimeters in length. So that's the kind of acquisition time. But this is one of those things as well where you get huge amounts of data, and it takes a very long time to go through, because as opposed to the other techniques where it's very focused and you know what you're looking for, you're just getting everything, and then you have to start and go through, and the research that was working on it, so that you just literally started searching for things and it can search for days. You have to leave it. So it's the post-processing that can be the really time-consuming part.
Yeah, it always is. Yeah.
Okay.
Okay, just to answer the question about how long it takes to make the measurement and what resolution you get, so they're related to each other. You have to scan the sample at the resolution you want, so you use very small beams. So if you can go down to 1 micron or even less than 1 micron resolution in your eventual voxels, you have to scan this many steps. So we do samples typically up to 5mm, 6mm diameters is feasible, but then with 10 or 20 micron resolution. So it depends how good a resolution you want as to how long you can do it in a reasonable amount of time scales of hours, let's say. Usually done at rather high energy for various reasons, because not have an absorption problem in the sample, and also you want to put the detector far away for some other reason of resolution.
So what, 50, 100 kV?
Normally 70, 100 kV.
Okay, thank you. We can all thank Eleanor again.